So we'll be starting off with a new chapter, rotational mechanics. Last class homework problem baki hai na? Or did we finish it off?
Baki hai.
Ha. Anyone got it? So the catch in this question, right, is velocity is perpendicular, in the force is perpendicular to the velocity. At any instant, if you see this is Fv, this is V, because of this thrust force, the force is always perpendicular. Since F thrust is always perpendicular to V bar, speed will remain constant. See, when you apply force, velocity should change. So that can happen by changing direction also. Right? So this is a special case where the direction is changing, where the speed is constant. So if the speed is constant, so this thing is kind of going in a circle. So this F here is providing the required centripetal force. So F thrust is equal to mass into centripetal acceleration V square by R. The thrust force will be lambda into U relative. Here mass will become M minus lambda T into V by R into V. So here the mass is changing. So what is happening here? Thrust force is constant, speed is constant, mass is changing, and radius of curvature is changing. So as this thing goes, it becomes smaller and smaller. The turn becomes sharper. So this would be lambda U by V M minus lambda T, and V by R is omega. So the whole idea is, since you asked me to find the angle as function of time t, think about it. The only thing till now, the only where we saw the angle in terms of time is what? Circular motion, isn't it? Omega. So that should be the hint, like somehow you have to create omega from this equation there. Omega is d theta by dt. Lambda u by v, 1 by m minus lambda t. So d theta is lambda u by v dt by m minus lambda t. 0 to delta and 0 to t. So this would be delta is equal to lambda u by v minus 1 by lambda m minus lambda t 0 to t. There, that's your answer. So the whole question starts from the point that the velocity speed is constant. Once you know speed is constant, then as it is rotating, what changes is omega. Have a look at the steps. So main thing, once you figure out that F is perpendicular to V, speed is constant, this force is responsible to centripetal acceleration, then it is just a matter of math. This is a question, where it is easy to solve, but it is little the starting point, it doesn't click. This thing actually, right, there is a problem like this in magnetism. We will see in 12th. Not exact same thing, thoda similar tha. So I was inspired by that problem and I said, yeah, why can't we do that for rocket thrust? It works. So this is what I keep saying, the idea is you can keep jumping between different chapters. Physics mein that is possible. Check it out. Yeah.
Sir, how did you get the idea that that F thrust is giving like the necessary centripetal force?
Think about it. It is, now you said F is perpendicular to V. Think about it. Till now, all the chapters you learned, where did you hear first time F is perpendicular to V?
Circular motion.
Uniform circular motion. So, and if F is perpendicular to V, this thing looks like it is going in a turn. So it is making some circle.
Okay.
But that circle ka radius is changing.
Hmm.
So So after that, once you got this thing, then you can start seeing actually I need to get omega from somewhere. Once I got omega, it is clear I'll get the angle.
Okay.
Yeah, but the starting point is that F is perpendicular to V. The moment I heard the word, the first thing I can think of is circular motion, isn't it?
Yes.
See, the questions are, it is always like that. If something hits you when you hear some words, that will hit you. And boss, ये chapter से start होगा. And second thing, you said delta is function of time t. That means you want angle changing with time. Angle changing with time never came in vectors, didn't come in kinematics, didn't come in NLM, friction, circular motion is the first time you saw. And not there in work per energy, not there in center of mass anywhere. So that is how we eliminate. See, it is like, instead of trying to find the answer, if you can actually eliminate stuff, that will be more easy to get the answer. Same thing in life also. We, try to select the good things. That is a little difficult. As long as you make sure you don't select the bad things, good things will take care of it. Kabhi hua, you go to the shop, there are 3 dresses and 4 dresses, you get confused which one to take. I mean, girls के साथ generally होता है. Boys का तो कुछ नहीं है. Whatever is there, we just take it and get out of there. So sometimes we go for shopping, right? My wife has the same problems. Like she finds 3, 4 things. Especially my mom has more problem. She goes to a shop, she gets confused. She sees 10 choices, she gets confused. I tell her, there are 10 things. Don't try to select them. Tell me why each one is bad. And humans are very good in, saying something is bad, isn't it? It is more difficult to praise someone. It is more difficult to, say something negative. So out of the 10 things, right, she starts saying, okay, ये अच्छा नहीं है paper, इसका cloth का quality नहीं है, ऐसे चलो छोड़ दो. ये अच्छा नहीं है, if you wash it, तो this will shrink, ऐसे छोड़ दो. So we keep eliminating. We'll end up with maybe 2 or 1. And then she will say, yaar, ye 2 last bacha hai. She's not able to find any more negative in both the things. Then she'll say, what to do? I said, take 2. Take both of them, right? Big deal. If you're unable to find between 2, and if you don't have money for both of them, then choose any one. It doesn't matter. But if you have enough money, then take both of them. That way helps a lot. Clear with this? This is what I keep saying about guessing options also. Don't try to select when you're guessing, don't try to select a correct answer. Try to find out what are wrong. If you can find the 3 wrong answers, the 4th one is right. So that's a human tendency to find negative things. Then use it to your advantage. That's what people don't realize. Why are you trying to select good things? It's very difficult to pick out good stuff. And we are experts in selecting bad stuff. So select the bad ones. Clear? And that is how you know which friends to talk to, which friends not to talk to, isn't it? Next one. Rotational mechanics. Quite an important chapter. Has a pretty good weightage. Generally, it is supposed to be tough, but till now, everything that I taught you, right, is for this chapter only. So we will go in a proper format, so you won't find it really that tough. Getting it? So only thing is you need to practice. So especially rotation, right? There are 3 important things, the basics you can say. Just like in laws of motion, if you remember, there are 2 basics. Anyone remembers what are those? In laws of motion, there are 2 basic things when we started. One is free body diagram, one is constraints. If you know free body diagram, if you know constraints, what is the 3rd step? Writing forces, horizontal, vertical, and solving. That was easy part, right? So same thing in rotation also, we have 3 parts. One is calculation of torque, one is calculation of moment of inertia, the third is the relation between rotation and translation. We can call it no slipping condition. So these are the 3 basics. If you know these 3 things properly, what to do with each, I think 70-80% of the chapter is in your hands. And the last part is angular momentum. That is little deadly, but that is still manageable. We'll see that also. So let's start off. Let's start off with a rigid body. We have done this in NLM. What's a rigid body? Straightforward definition. The distance between 2 points remain constants. If you take any 2 points on a rigid body, do whatever you want. You can't change the distance. It looks very simple definition, but it's a very powerful one. What this simply tells you is the body cannot be deformed. You can't compress, you can't elongate, you can't do anything to the body. Now, so if you can't change the distance between 2 points, let's say I give you an option, okay? The distance between you and me is fixed, okay? But I am saying you're moving. How is that possible?
You are
The
also
distance between. No, I'm at rest. Alright, think now. Distance between you and me is fixed. I'm at rest, but I'm saying you're moving. What is the only possibility?
In a circular motion.
You can't
circle.
stretch. You can't stretch. You can go in a circle, isn't it? Imagine there's a pole here, and if you are here, if I tie you with a rod, and if I say you're moving, there's only one way you can go in a circle, isn't it? You can't go away, you can't come closer because the rod cannot stretch or compress. The only way you can go is in a circle. So therefore, so the motion of one point, therefore, the only way one point on the body can move with respect to another is a circle. So if you give me a rigid body here, and if you say this is point A, if you say this is point B, and if you say this is point C. So if you ask A, how is B going? A will say B is going in this circle, and it will say C is going in this circle. So A thinks B and C are going in circles. Now something more interesting happens. If you take a line AB, if you take a line CD, if I say line AB rotated by theta, you can be sure even line CD rotated by theta. If any line if a line on a rigid body rotates by theta, then every line on the rigid body rotates by theta. How is that possible? If I join these 4 points AB and CD, I'll get a quadrilateral. If this line rotates by theta, if CD does not rotate by theta, will you still get the same quadrilateral? Is that making sense? So if you say AB rotates by theta, C and D who are not related to A and B you can be sure CD also rotates by theta. That means you can make a statement here. Angular velocity of all the lines on a rigid body is same. We call this thing angular velocity of a body. It's same for all lines. Now see, in circular motion, we studied angular velocity. That and these are completely different. Angular velocity of a body is a different concept than angular velocity of a particle. In circular motion, what we studied was angular velocity of a particle. This is angular velocity of a body. Remember, it is the same thing. Is rotation same as circular motion? You're
Yeah.
getting it? Rotation was different. God, what? Yeah. Rotational motion is defined for a body. So that means when you say a particle going in a curvilinear motion, can't it be translation? वो भूल गया क्या? The rod which is hinged here, it was going
Those points
giant
A,
wheel
B, C,
wala.
D.
Then
Yeah.
if you see the particles are going in circular motion, but it is a translatory motion.
Got it. Yeah.
Circular motion is defined for particles. You need to understand clearly here. If you observe, before center of mass, we never bothered about the dimensions of the body, isn't it? The meaning if I had given you a body like this, mass m, and if I have given a body like this, do you really think both of them will move the same way? This is going to topple, right?
Yes.
But we never cared about it. We always treated them to be a particle and we solved the entire problem. You can't do that anymore. So rotation is defined for a body. Circular motion or angular velocity of a particle is defined for a particle it is. So let me show you that example also. Everyone clear with the switch? So when you say angular velocity of a particle, so what we studied till now was angular velocity of a particle. You treated the whole body as a particle and you studied. Depends on the observer. Example, when you took a particle going on a circle with speed u, this angle was theta. This angle was how much? Theta by 2. Radius is r. So if you ask O, what is the omega of the particle? So omega with respect to O was u by r, which is d theta by dt. But same thing, if I ask you angular velocity with respect to A, it is d by dt of theta by 2. Every time it rotates theta in O ka frame, A will think it has rotated only half the angle. So this is half of the angular velocity of O. Did you see? The angular velocity change depending on where you are. This is angular velocity of a particle. Angular velocity of a body is defined for bodies, especially rigid bodies. So angular velocity of a body is same. Is that making sense? So if someone asks you this question, a particle is going somehow. Okay? Particle is moving with some velocity v. Find the angular velocity. You should ask me, sir, who is looking at it? But if I say angular velocity of a body, it doesn't matter where you stand. You will think everything is rotating with omega. Is that making a difference? If I say find the angular velocity of a body, you need not ask me about which point. No matter where I stand on the body, I will think it is same. But if I ask you angular velocity of a particle, you need to ask me, sir, where are you standing and observing the particle? So this is the first difference that you should know between angular velocity of a particle and angular velocity of a body. Both are not same. Have a look at this. Clear? Let's see a question. This is quite a useful thing actually. Later on we will see. Since we know no matter where you stand, you will see same omega, you will see same alpha. That makes your life easy. Now, based on this, we can frame questions. Top view. We have a disk. The radius is r. So we have a point B here. B is going upward. VB is 2 meter per second. J cap. This is point A. The velocity of A is pointed towards B. This O is the center. I'll just call it C. So at this instant, velocity of B is 2 meter per second J cap. Velocity of A is towards B. Find velocity of A, find omega of the disk, and find velocity of the center. Now understand one thing. These kind of velocities, right, are possible only when the body, right, is rotating and translating. The disk is rotating also and going also. If the body is translating, velocity should be in the same direction, isn't it? So if you observe here, it looks quite weird, like how can A ka velocity be towards B and how can B go somewhere else? This is possible when bodies are rotating and translating. So using this data, you have to find out velocity of A, velocity of the center, and omega of the disk. Get this. Take a minute. Give it a try. I'll show you, and then I'll give you one more like this. This is simply based on circular motion and rigid body constraint. We won't be having a class on Friday. Huh? This week, there's no class on Friday. We'll directly catch up again next Wednesday. In case you guys are planning something for the new year, you can plan. What happened, Ayasha? You made some big plan? Hey. No, Arjun, that is wrong. That is for what? VA, kya?
Yeah.
No, re. So you got little more actually. ज़्यादा आ गया आंसर. Take a minute. Do visit IIT Bombay if you have time today or tomorrow, day after tomorrow. If you've already seen, then fine, but you can go and see. I think there'll be some robo wars also. They'll put some robots in their fight and they destroy each other. That is something interesting. Let me help you with one question. See. First thing, it's a rigid disk. So this is point A, this is point B. If you draw a line joining A and B, so velocity of VA is in this direction. VB is this way. This is 45, so this is also 45. So this would be VB sine 45, and this is VB cos 45. So first thing, since it's a rigid body, what should happen? Velocity along the line should be same. So VA should be equal to VB cos 45, isn't it? If the velocity along the line is not same, what will happen? Either the rod will stretch or rod will compress. Remember rigid body constraint? If you draw a line, the velocity along the line should be same. Velocity along the line must be same. Or else the line will stretch or compress. So from here we get VA is equal to 2 cos 45, that is root 2 meters per second. You want to vector form, VA bar will be minus root 2 cos 45 minus I cap plus J cap. And what about omega? Omega, if you remember, this is also comes from circular motion here. The relative velocity perpendicular to line joining by distance between them. Perpendicular to line AB, the length AB. So here in this case, A has no component, so this will be VB sine 45 by distance is R root 2. So omega will be 2, 1 by root 2 by radius is 1, and this is root 2. That is 1 radian per second. Which way? Clockwise. How did you know that? You can clearly see in that. This is the component of VB sine 45. Meaning it's going to rotate this way. So that means the disk is rotating this way with omega. Again, I didn't teach you anything new.
Omega vector is like into the plane, right?
That is fine. No? Minus k.
Oh.
There we got omega. This comes from circular motion. This comes from loss of motion rigid body constant. I didn't teach you anything new. These were repetitive. How to find velocity of the center? Fine, I'll give you a minute. See, now there are two ways to do this. You can go back to again NLM and do that. You can assume this is Vx and Vy, and you can take components along this line and this line. That is little lengthy. But let me ask you, if an observer is standing on B, and if you ask him how C is going, what will he say? If you stand on one point on a rigid body, and if you ask what is other point doing, what will it say?
Circle.
Going in a circle. That was the whole story we did. So that means B will think this guy is going in a circle with R omega. B thinks C is going in a circle. Therefore, velocity of C with respect to B will be minus R omega I cap. So velocity of C in the ground frame will be velocity of C with respect to B and velocity of B with respect to ground. And I already know B, how is it going? So R omega is nothing but R is 1 and omega is 1, so minus I cap. So this is minus I cap plus 2j cap. You're getting it? So if you stand on B and if you look at C, I know it is going in a circle, but B himself is going straight. So if you look at the final question, this is what is happening. This disk is going this way with a velocity minus I cap plus 2j cap. And this whole setup is rotating with omega, which is 1 radian per second. So this is how the motion of the disk is. It is translating in minus a plus 2j in the second quadrant, and it is rotating anti-clockwise. Check it out. So this is how you can get that answer pretty fast. Clear, everyone? So if you stand on one point whose velocity you already know, it becomes easy from that point of perspective. Let's see one more like this. Any doubts on this, please ask me. So I used rigid body constraint, then I used circular motion omega relative between two particles, and then we used angular velocity of a body. Clear, na? Abhinav, Udyan? Clear? Maulika, Ali? Clear? Perfect. You guys try this. Equilateral triangular plate. Side A. This is point A, which is going with V. This is point B, which is going like this with some velocity VB, which I don't know. This angle is 60. This is point C. Find VB, find omega of the plate, and find velocity of C. Get this? No, this is the same as the previous one. I just changed the shape. Wait, I'll do one thing. Let's make this 30. Hmm. Let's make it 30. Means B is vertical, A is horizontal. Hmm. Yeah. Okay. V by root 3, yeah. So draw the line along AB. This would be 60. So this would be V cos 60. This would be VB cos 30. So V cos 60 is VB cos 30. So VB will be V by root 3. Omega will be V sine 60 minus of minus VB sine 30. This is V sine 60. Should take the perpendicular component, and this is VB sine 30 by distance between them is A. V root 3 by 2 plus VB is V by root 3 by 2 by A. So V by 2, that is root 3, 3 plus 1, so 4 by root 3 by A. 2V by root 3, that's your omega. This way clockwise. Check. Omega, simply take the 2 points, find the velocities perpendicular to the line joining, and divide the distance between them. How to find C? I think B is the best point again. If you stand on B, B will think C is going in a circle like this with R omega. In this case, it is A omega minus J cap. Isn't it? That's what B thinks. The velocity of C with respect to B is minus A is A only. Omega is 2V by root 3A. The velocity of C in the ground frame velocity of C with respect to B plus velocity of B with respect to ground. Minus 2V by root 3. And B is going up, so VB is again V by root 3. Minus V by root 3 J cap. Check. Is that making sense? You could have done this from A ka frame also, but I felt B is looking more easy. Because if I do A ka frame mein, then A will think it is going in this circle. Then C ka velocity will come this way. Then usko unnecessarily components lena padega. You would have got the same thing though. Check it out. I can ask you find the velocity of centroid also. Now I can ask you any point. But I hope everyone is getting the idea here. You know how to find omega. Once you get omega, just stand on some point whose velocity you already know and just look at any other point. It will go in a circle and then just add it back. Clear with this? This is one type of models based on the rigid body constraints and rotation involved. We couldn't do these kind of problems before. Clear? Any doubts on this? There. Next thing, torque. Going ahead. Ali, clear na? Neil? Vartika, clear so far? Perfect. Next thing. Torque. Symbol is tau. And a tau ka symbol is different, but I write like this. So you can use whatever symbol you want. So what is torque? Torque is a body continues to be in state of rest or uniform rotation until and unless force is applied upon it. Until and unless torque is applied on it. It's the same definition as the force actually. There the definition of the body continues in a state of rest or uniform motion. So if you want a body to rotate, what you need is not force, but something called torque. So you need to understand torque and force are not the same thing. They're related, but they're not the same thing. So whenever someone asks you if you want to rotate, the quantity you should see is torque, not force. Now, before jumping into the torque part, we need to define something called axis of rotation. This is one major difference, between NLM and rotation. In NLM, if I ask you, there's a force F 10 newtons, I don't care where it is. F is 10 newtons, discussion closed. But in this case, if I say force is 10 newtons, then you have to tell me, boss, what is your axis? Every time you have to ask your axis. Without defining that axis, you won't be able to go ahead with the problem. So what is this axis of rotation? If you consider a body which is rotating, you'll observe that different points on the body will go in different circles. Consider a body rotating. We observe move in different circles. The line joining the center of the circles. So if you take all the circles and if you join all the centers with a line, what you get is axis of rotation. The line joining the center of the circles is the axis of rotation. Best example, look at your door. If you look at the door here, so the door rotates about the hinge. The edge of the door, right, is an axis of rotation. So if you look at this point here, A, this is going in a circle here, so this is the center. If you take any point here, B, this is going in a circle, this is the center here. So if you join them, all the centers will be on the line. The same thing, your ceiling fan. If you see that rod which is there vertically, this is your axis of rotation. So that supporting rod is the axis of rotation. And if you look at this thing, these are going in a plane. So this is the fan rotates in, rotation is in plane. This is the plane of rotation. So plane of rotation is different from axis of rotation. Both are perpendicular basically. So if you use right hand thumb rule, the plane of rotation, right, will be the curl of your fingers, and axis of rotation will be the thumb. So if you think about this, this is actually similar to 1D. Just like translation, we had 1D, 2D, 3D. Even in rotations, you have multiple rotations. I'll show you how it is. This is similar to 1D. This is what we'll be studying for most of the time. Have a look at this page. Axis of rotation. So all these are small things. Like they look kind of obvious, but when you don't define them properly, right, when the question suddenly becomes difficult, you will have no clue what the hell is happening. That's how the confusion starts. When you don't know about axis, generally that I observe, angular velocity of a body, angular velocity of a particle, people have no idea. Torque, they know what is the axis of rotation, but they can't define properly what it means. And you'll see why they'll get stuck in the next part. Clear with this? There's something even more powerful than axis of rotation, point of rotation. So point of rotation is simply, right, it is a combination of multiple axes of rotations. It's like 3D motion. It's a combination of axes of rotations. Think of like this. Let's say X, Y, and Z. So let's say we have some disk like this. So this is rotating in one direction, and this whole setup is again rotating in another thing. So if you see, there are two axes of rotations here. Self-rotation and the whole revolution kind of thing. But a best example would be, so this here is a point of rotation here. A better example would be this thing. Your shoulder is there. Your shoulder, when you rotate your hand, the shoulder is actually a point of rotation. Shoulder is a point of rotation. Think of like this. So if you're standing, let's say your hand is like this. If you can rotate your hand like this, you're getting how it is? You're rotating in front of you. Getting it? It's like rotating in front of you. If you see, the plane of rotation is XY plane. Whereas the axis of rotation here would be into the plane. This is your Z axis. So Z axis is your axis of rotation. So you can move your hand like this. Or You can put your hand like this and you can rotate the hand like this. I know you can't complete a full circle, but you can rotate the hand in front of you, put the hand in front of you and rotate left and right. So here the plane of rotation would be XZ plane. And axis of rotation will be like this. You're rotating about y-axis. The third thing, if you put your hand straight and if you rotate like this, you're going like this, up and down, see the. So here, this thing would be a YZ plane ka rotation, but the axis is along x-axis. So you're getting? You will be able to rotate in all three directions, x-axis, y-axis, z-axis. So your shoulder is actually a point of rotation. Your door is there. If you observe, you can rotate your door only in one plane, isn't it? Either you can rotate that towards you or away from you. You can't rotate the door up and down. You're getting the difference? See, think of like this. The book which I'm holding here, if you can see, this is a point of rotation, meaning I can rotate like this, I can rotate like this, I can even rotate like this. Dekha? 3 points of rotations, front, back, left, right, and rotation. There are 3 points of rotation. But the same book, if I suddenly catch it like this on the edge, the grip, then you're stuck. You can only rotate front and back. If I try to rotate like this, it is not going to rotate. Getting it? This rotation is not restricted. You can't rotate this thing. Is that making sense? Point of rotation and axis of rotation. So if you know how to do axis of rotation, it is simply 3 times in 3 different directions will give you point of rotation. And if you look at this, we have done this in circular motion also. So here, the curl of the fingers is along plane of rotation. Thumb indicates the axis of rotation. We can use right hand thumb rule. So right hand rule will give you the direction of the axis, which way it is. Have a look at this page.
So,
Yeah.
so the doors in our room, why can't we rotate it like completely in a circle?
Which
Like
one?
the doors, the
You'll
most,
break it, record. You're blocking the hinges now. Look at this example. Can you really rotate your hand like this?
no,
Your head will block you now.
yeah.
Once you go till here, you are going to block. It's not a complete thing. You are free to rotate up to an extent. That is because of the physical limit, right? So if you see in real life, you can never get a point of rotation.
So
These
basically,
mechanical systems, you can have partial rotation. You can't have a full rotation in all 3 planes. Something will block, right? When you're making mechanical parts.
basically you're attaching it to something that
Attaching to something, yeah. The moment you attach something, you're restricting it. Clear? Next thing. Torque. So this is the first important thing. Calculation of torque. So there are 4 cases here. Now this is all experimental. Case 1. So this is how we define this is how we show axis of rotation. We show a line and then that arrow thing there. So we have a rod here, and let's say you're applying a force F. This force F is passing through the axis. So this is what we observe. F bar is passing through axis. So we observe torque is 0. It does not rotate. So if the axis force passes through the axis, torque is 0. Case 2. Let's say you're applying force F. It is perpendicular to the rod and it is in the plane of rotation. This thing, again, experimentally people calculated this thing. They found out if you take this distance to be R, the torque is R into F. Isn't it? It is more easy to push the door. For example, if you have a door like this, isn't it more easy to push the door here than here? The farther you are from the axis, more easy it is. Why all that? You just try to take a, some weight there, some bottle or your water bag or something. You try to, catch it like this and try to catch it like this, stretching your hand. Isn't stretching more difficult? Because the further the distance, the more torque will come. So case 2 is when the force is perpendicular and in the plane of rotation. The case 3 will give you the actual thing. The force F is at an angle theta. And this is your R bar. You can clearly see here, you can resolve F into two components. F bar is at an angle theta. To the rod and in the plane of rotation. We end up with torque is equal to R F sine theta. Because if you resolve this into two components, F cos theta will be like case 1, F cos F sine theta will be case 2. So we get torque is equal to R bar cross F bar. Important thing here, R bar is a vector from axis to the point where force is applied. This is important trick. Most people goof it up. Most people think the moment they see R bar, they think it is a position vector. R bar is not the position vector. R bar is a vector from where the axis of rotation to the point where the force is applied. I think we'll remove the lines. That is better. Clear? Have a look at these three cases. Clear? Now, so how do we will simplify this form into a better format. And listen to this carefully. Yeah? This is the technique we will use to find torque, and later on, this is the technique we use to find angular momentum multiple places. So the torque, you wrote it as RF sine theta. So what we can do here, you can split this into two parts. You can do it two ways. So if this is your force vector, this is your r bar, extend the vector, make this angle theta. This is your axis. You can resolve the forces F cos theta and F sin theta. So here F sin theta is the perpendicular component. So we can write this as R into F perpendicular. So instead of every time trying to find the angle and all that stuff, you can simply resolve the forces along the line and perpendicular to R bar. So keep R as it is and divide the force into components. So you can write torque as RF sin theta, or you can also write this thing torque as R sin theta into F. This is R bar. This is theta. Extend the line. So this is the technique here. Extend the force vector and drop a perpendicular. This would be your axis. So from here, if I drop the perpendicular here, this is your perpendicular distance. This is theta. This is r sine theta. Means you can also write this thing as perpendicular distance into f. So the main idea is this. If you keep r constant, divide f into components. If you keep f constant, divide r into components. Getting it? Split one of them. Keep the other one constant. Both will give you the same answer. Both will work. Now, which one to use is your comfort. Sometimes exam something will strike first. So use that. Whatever you find, is convenient for you. But generally, this is the thing which comes a lot that I observed, but nothing wrong with using the other one also. So this will give you the magnitude. Now you know how to calculate magnitude for a torque. How do you get the direction? Listen to this thing once. It's easy. It's for direction. Assume R bar is a rod. So think R bar is a rod and see which way it rotates. And see the rotation of the rod. So when you apply force, see which way it rotates. See the rotation. See its rotation. And use right hand rule. Example. Let's say if this is your R bar, listen carefully, and let's say this is the F bar. So this is your axis. Simple logic. If R bar is a rod, if this R bar was the rod and this was the force, tell me one thing, which way will it go? Right or left? Clockwise, anti-clockwise, which order? If you apply force this way, will it go to the right side or will it go to the left side? It will go to the right. This must we can see and tell, right? It goes to the right. Now, if it is going right, meaning what direction is this? Anti-clockwise. Anti-clockwise means what? Plus k cap. Makes sense? You just need to see which way it is going, right or left. Once you get that, you'll get the rotation ka direction. Let me take one more. Let's say this is R bar. And let's say someone is applying F bar like this. Now, which way will it go? If this was the rod, I know it will go this way. That is clockwise. So just assume as if R bar is a rod fixed at the axis. And when the force is pushing, just see which way it rotates. Clockwise, anti-clockwise, use right hand thumb rule. So this will give you the magnitudes. This will give you the directions. You know these two, you know how to find torque. Please have a look at this page. Anti-clockwise should be K. Matlab, what is clockwise, anti-clockwise? It depends on where you're standing na. For example, look at your fan right now. Tera fan ka rotation kya hoga? What is your fan ka rotation? Downward, na? It is downward. So what is it K cap plus K cap? Depends on what did you choose that axis. If you ask me, I'll say it is minus J cap. Someone can say, no, sir, I'll take that as that axis. Okay, then it will be minus K cap. So that depends on you. Here, I'm just showing on a paper, na? So into the plane, out of the plane, we took it as Z axis. Clear with this, everyone? Let's see a question. There, now you know the format to find torque. A force F bar 3I minus 2J plus 4K acts at the origin. Find torque about point A whose coordinates are 1, 2, 3. Get this. Easy one. Just give it a try and get some water and come. Let's see how many of you fell into the trap. What is R bar? I cap plus 2J cap plus 3K cap, right? That is evil laugh. Meaning it is wrong. So what? Definition of R bar क्या था? पढ़ो एक बार. R bar is a vector from the axis to the point where you applied the force. Here, where are you applying the force? The force is at F bar, is at the origin. Where is the axis? Point A is your axis. So what is R bar? R bar is a vector from the axis to the point where the force is applied. So R bar is AO bar. It is not OA bar. Getting it? This is happens a lot, you know. Remember work per energy mein integral F bar dot ds. What is ds? What is ds? Displacement of point of application of force. It is not just displacement. So you have to be very clear what is the definition. When your definitions are messed up, things will go wrong. So AO bar will be minus I cap, minus 2J cap, minus 3K cap. If you have not done this, you will get a minus sign option answer, and that also will be there in the exam. So be careful. Simple mistake. It would cost you 4 marks. So torque is R cross F bar. Everyone knows how to do 3 into 3, right? I assume. So I, J, K. R bar is minus 1, minus 2, minus 3, 3, minus 2, and 4. So this would be I into minus 4 plus 9, 5, minus 4, 5, minus J. Wait, I did that wrong. Minus 2, 4, minus 8. minus 8, minus 16, minus 14. Minus j is minus 4 plus 9, that is 5. Plus k is 2 plus 6, 8. Check. Minus 14, minus 5, 8, right, Anusha? Yep. People who forgot that minus sign, you'll get an answer in the reverse. 14i plus 5j minus 8k. That will be there in the option. This would be a proper mains level question. Easy? Be careful. Definition of R bar, Molika. Tell me, what is the definition? Read, what is the definition? Vector from where? Axis to the point where force is applied. Now, here, where is the force applied? At the origin. Where is the axis? Here. The vector should go from where to where? A to origin. So head is at the origin, tail is at the A bar here. This is your R bar. Got it? R bar is not position vector. Just remember that. Okay? Yeah. Yeah, that happens because the moment we see R bar, the brain signals position vector, position vector, position vector. So that's what happens. Be careful with the definitions. Next thing. Equilateral triangle.
So can you go back for a minute?
Hmm.
Yes, so thank you.
Side A. F1. F2. F3. F4. 5. O is the centroid. Find the torque due to all the forces about the centroid. Due to F1, F2, F3, F4, F5. About O. I'll show you one. Listen. What am I expecting from you? So this is the force F1. This O is the centroid. Extend the force vector. Drop the perpendicular. So this would be a perpendicular distance, which is, remember, centroid divides in the ratio of 2:1. So ये होगा 2/3 of height, which is A by root 3. So torque due to F1 will be perpendicular distance into magnitude. And how will this R bar rotate? If this is your axis, you can see it rotates in this way, which is clockwise. So the direction is minus k cap. Understood how we got the magnitude and the direction? So like this, you have to find me for the remaining 4. Get it? Give me the magnitude and the direction. I did for F1, you do for 2, 3, 4, 5. Get them. You got a 1 to 2 minutes. What is F2? F2 root 2 by 3. Root 3 by 2, I guess, no? This is F2, this is centroid. Extend the vector, drop the perpendicular. So this is your R bar, which is A by 2 root 3. And the direction would be this way. So torque due to F2 will be A by 2 root 3 into F2 and direction is plus K cap. Torque due to F3 will be 0, passing through axis. Get the remaining two. Okay, you took H by 3. Get F4 and F5. Anyone confused with this, please ask me. You should definitely know how to calculate torque. You mess up the magnitude direction. If you don't know how to calculate torque, you can forget about the rest of the chapter. It's very important. Like, this is the fundamental thing. Now see F4, right? The problem with F4, I can take the perpendicular distance thing, but for some reason, I don't know, I'm not getting a feeling you can calculate, but it looks more messy. But if you draw a line from here through the centroid, this angle will be 30 degrees. Angle bisector, isn't it? So this is also 30 here. So I think I can use the other method, divide force into components. F4 cos 30 and F4 sin 30, and this is the perpendicular distance here. How much is that? A by 2 root 3. So torque due to F4 will be A by 2 root 3 F4 sin 30 minus K cap.
Sir, but over here you had already calculated the upper wala distance, so we can do it directly also, right?
What is that? Yeah.
You had already calculated for the first part.
Then ये कैसे calculate करेंगे? You wanted this thing, na?
So from the center to the top will be A by 2, so that minus A by 2, na?
कर सकते हो, but you can do that. I just wanted to show another thing. That's it.
Okay.
There's nothing wrong. Both will get the same answer. Like I'm saying, which one is more comfortable? I didn't feel good calculating such a small thing. But if that strikes more comfortably, do that. Nothing wrong. F5 cos 45, F5 sin 45. The torque due to F5 will be same thing. A by 2 root 3 F5 sin 45 plus K cap. Please check. I'm leaving the simplification to you. Magnitude and direction. Everyone should get this thing. A by 2 root 3. How did I get? It's a big doubt now. Centroid divides the triangle in the ratio of 2:1. Right? Clear, everyone? The total height is 8 root 3 A by 2. So this will be 1/3 of root 3 A by 2. That would be A by 2 root 3. Do remember that. This will come a lot. Triangle Comes in at least 6-7 chapters more. Easy, got this thing. Let's see one more like this. It's a regular hexagon, side A. This is point A. F1, F2, F3, F4, F5. Find the torque about point A. A is a corner. A is not the center. Same question, I just change the shape and 5 forces. Find the torque about this point A due to F1, F2, F3, F4. F1, F2 are horizontal, F3 is vertical, F4 is pointing towards this corner, and F5 is pointing towards this corner. Get this. I think if you got this, then we can be sure you know how to calculate torques. F1 is easy. It's more of a geometry, everyone. More of a geometry. Once you figure out the geometry, things will fall in place. For people who forgot, a hexagon is made of 6 equilateral triangles. So this is your F1. Extend the line. So from point A, if you drop the perpendicular, this is the perpendicular distance. This is 90, so this is 30 degrees. Total is 120. This is A. So our perpendicular will be A cos 30. So torque due to F1 would be A cos 30, F1, and the rotation would be this way, which is clockwise minus K cap. Similarly, if you take F2, extend the line and drop the perpendicular, I didn't draw this properly. This also will be A cos 30 by symmetry. The torque due to F2 will be 2 times A cos 30. Into F2, this will be also minus K cap. And if you look at this guy, F3, this will directly pass through here. So this is the perpendicular distance, A. So torque due to F3 will be A into F3. That would be plus K cap. Check. Now what's left is F4 and F5. Get them, F4 and F5. Check F1, F2, F3. I wrote that answer. Check. You can check your answers up to F3 here. F4, F5. Try. I'll give another minute. F4. Any ideas? You want a perpendicular distance now, so from here drop a perpendicular. Now be careful, this won't be center. That won't be center, because if you draw to the center, that angle will be 60 degrees, equilateral triangle. That is not center, it is something else. If that is 90, I know this is 60 and this is 30 and this is a, should be a cos 30. So torque about F4 will be a cos 30 F4, and if you see, this rotation would be this way, minus k cap. Check. And this is even more interesting actually. If you see, this is 120, this is 30 and this is 30, because it's a isosceles triangle. That means this is already 90, isn't it? So this is already perpendicular distance. इसके लिए कुछ करने का जरूरत नहीं था actually. This is already perpendicular. The torque due to F5 is A into F5. That would be again plus k cap, minus k cap. Please check the magnitude and directions. Anything you're not convinced, please ask. If you can handle this much, you know how to calculate torque. That is the first thing. Clear? Take a break. Come back by 7:05. Make it 7:07. Any doubt so far? You can ask me anything that you didn't understand in this, the previous problem. Anything you're not clear? If you're clear, you can take a break. Any doubts on this perpendicular distance, direction, anything you're not clear on this page?
Sir,
Ali, clear na so far? Haan, Malika.
sir, can you tell me what was done in the start? I came a little late actually.
Starting वो थोड़ा अलग ही है. It is not based on torque. When did you come?
I
You came?
joined it. I joined in 5:36 or something.
No, वो नहीं है. You topic कहाँ से सुना तो वो बोला ना.
वो ये talk से.
You're not there for this thing.
No, I was there.
तो ये starting कुछ नहीं. Just I was defining rigid body का definition था.
अच्छा.
We're just
Okay,
talking about angular velocity of a body and angular velocity of a particle.
Okay, sir. Thank you.
बस वही था. F4 you are getting different by resolving forces F4, how did you resolve, God? You have to resolve like this, now. What is this angle? 30, right? This is 60. F4 cos 60, F4 sin 60. You should take F4 sin 60 into this perpendicular distance, which is 2a cos 30. Check करो. ठीक है अद्रित? Check करके देखो. You should have got that F4 sin 30 into 2a cos 30. Or maybe did I goof up somewhere here? Looks right. Okay. Chalo, back by 7 then. Next thing is rotational equilibrium. Anusha, you're saying something? F4, you're getting the same or something else? Okay. Rotational equilibrium. So what is rotational equilibrium? If the net torque acting on a system is 0, body is said to be in rotational equilibrium. Now, if body is in rotational equilibrium, torque about any axis is 0. Remember, just now we calculated, depending on which axis you're standing, you get different torques. But if you say body is in rotational equilibrium, you need not ask me about which axis. Reason, think about it. Let's say about a certain axis, if it is not 0, that means what? It is rotating in that frame. And we have proved it in the beginning. If you rotate in one frame, you'll rotate in every frame. So if you say you're in rotational equilibrium, you're not rotating in a particular frame, then you should not rotate in every frame. Is that making sense? So if I say body is in rotational equilibrium, it doesn't matter. You take any axis, torque will be 0. Fair enough? So that is important. So in rotational equilibrium, you need not ask me about which axis. Second thing is couple. Couple is nothing but torque due to equal and opposite forces. So for a couple also, right, you can take about any axis. Torque about any axis is force. So this is any one force into distance between them. Net force, it will be 0. So example, it would be something like this. So let's say 20 Newton. 20 Newton, and this is 3 meter. Then torque due to this couple is 20 into 3, 16 Newton meter. So same thing with the couple also. Whenever they say there's a couple of so and so, you need not ask which axis. You take any axis, it will be the same. We never had this problem in translation. If I say force F is applied, we never bothered about anything else. But torque means you have to be careful. If I say find torque, first question you should ask is, sir, what axis you are talking about? Clear? Next thing.
So would that be two equal and opposite forces?
हाँ मतलब equal and opposite forces. ठीक है. You want me to write 2? We can do there. How does the couple enable the body to rotate? Means what are you asking exactly? When you open your tap, what are you doing? It's a couple. And you open your bottle cap, it's a couple. Try to open your, this thing, bottle cap with one finger. You're putting equal and opposite force. There is no translation, but there's only rotation. Right? Next thing is a hinge. This is again one common thing which keeps popping up everywhere. So we will define it before. So hinge is simply, it is a point about which the body rotates. So normally this is how the hinges ka diagram is given. So this point is your hinge. It's a point about which body can freely rotate. So basically what happens with a hinge, right? The force can be in any direction. So for convenience, what we do now, that any direction, how do I know what direction? So in order to get rid of that confusion, while drawing an FBD, anytime you see an hinge, always write NX and NY. Because any force can be divided into two perpendicular components. So you do that from the beginning only. Draw two perpendicular components at the hinge. Example, let's say we have a rod hanging like this. The only condition is they should be perpendicular. I don't care how you draw. You can draw NY like this, NX like this. Or you could have drawn NY like this and NX like this. So if they ask you what is hinge reaction, you should give NX square plus NY square. This is the total hinge reaction. NX and NY are simply components. So the main idea, whenever you see a hinge in a free body diagram, put NX and NY. And if they ask you to find hinge reaction, he's asking you to find root over NX square plus NY square. Because the hinge force could be in any direction. So we take care of it from the beginning. This is what makes actually this chapter, not, I wouldn't say difficult, but there are small, too many things are there. Clear? Got it? Next thing. So how do we solve equilibrium problems?
Yes, sir. Thank you.
Steps to solve equilibrium problems. Choose your system. And draw an FPD. With appropriate symbols. Second thing. Apply F is equal to MA along two perpendicular directions. In this case here, A is 0 because it is an equilibrium. So later on, we will see when things move. But for now, things are not moving. Third, calculate torque about any axis and equate it to 0. Preferably here, now see, since you can take torque about any point, preferably choose an axis where maximum forces pass through. Because if maximum forces pass through, the torques will become 0. Your symbols will be less. Mathematical equations will be a little easier to solve. Again, this is not a compulsory thing, but more of a convenient thing. If you can choose a certain point, your life becomes easy. Max forces pass through. Solve the equations. Have a look at this. Let me show you one example. Clear? Let's see a problem. Can I turn the page? Malika, clear so far? Vidyut, Rehan, Rakshika, clear? Yasha, clear now? Let me take an example. So we have a rod here. There's a string here and there's a string here. Mass M length L. Let's say this is 2L by 3. Now, if you just use NLM, you'll observe you'll not get any answers. So the question is find T1, T2. Step 1, choose your system. Here my system is a rod. Draw the FBD. T1, T2. The weight will act at the center of mass. It would matter now. You have to put the weight at the proper places. This distance is L by 2. Now, vertical direction forces T1 plus T2 is equal to mg. Next thing, take torque about any point. I will choose this corner here. So torque about axis A will be torque due to T1, torque due to T2, and torque due to mg. There are total 3 torques. Total is 0 because it is in equilibrium. Torque due to T1 will be 0. Why? It passes through axis. T2 ka torque will be, so if you look at this thing, T2, this is the perpendicular distance 2L by 3. For mg, this is the perpendicular distance L by 2. So torque will be T2 into perpendicular distance 2L by 3. Direction, if you see T2 is rotating upwards, so that is plus K cap. mg perpendicular distance is L by 2. Direction minus K cap is equal to 0. Later on, we'll stop writing this, but for now, I will write detailed. So we get T2 into 2L by 3 is equal to mg into L by 2. T2 is 3 mg by 4. And I get T1 is equal to mg by 4. Without the torque equation, you would be stuck with only this one equation. You can't do anything. Check it out.
So like if you're not getting that, we know from the diagram that T2 has to be greater than T1, right?
How do you know? You're feeling it as. Proof kya hai?
It's balancing the weight on the right now.
Fine. So,
No, like if we don't get the correct answer, at least we know that T2 should be greater than T1.
that much you can guess. But you know how to do.
Ah,
Clear? Let's see a question. I'll give you something similar. Now you try. Have a look at this example. Any doubts? FBD, torque, equation solve. Clear? Now you guys try this thing. We have a hinge here. This is theta. This is tension. This is a rod of mass and length L. Find tension and the hinge reactions. Okay. Right, I'll give you a minute. Tension, theta, T cos theta, T sin theta, mg, ny, nx. Forces horizontally, T cos theta is equal to nx. Vertically, ny plus T sin theta is mg. Now here I'll take the torque about the hinge. You can take any point, torque due to nx, torque due to ny, torque due to T cos theta, torque due to T sin theta, torque due to mg. Like I said, later on we'll stop writing, but for now, chalo, we'll write 0, 0, 0. They're passing through axis. T sin theta ka torque will be T sin theta. Perpendicular distance is L. Direction is plus k cap. mg, perpendicular distance is L by 2 minus k cap. So from here I get T sin theta is equal to mg by 2. If T sin theta is mg by 2, this also should be equal to ny. Ny aa gaya. Tension is mg by 2 sin theta. And next will be T cos theta, so mg by 2 cot theta. Check. That's it, straightforward. Draw the FBD, write the equations, force equations, vertical, horizontal, write one torque equation, solve. Let me give you any type of question. This is the process which is in equilibrium. If you see, the only new thing you learned is torque, isn't it? Force equations, so you know. Free body diagram, you already know. This is the reason, if you see, we kept a lot of emphasis on drawing FBDs properly. And this is the reason, if you see, some people have this habit. You ask them to draw FBD, they'll put a point and they'll draw the forces on a point. That's a bad idea because the distances will get messed up. So when we drew FBDs, right, we learned it like that only. We always do the proper FBD. Even though distances never mattered, now they'll start mattering. Clear with this? Let's see one more. Turn the page. Next one. smooth wall. This is a standard problem. We have a rod here, mass m, length L, angle theta, ground is rough. Equilibrium. Find all normal reactions in the friction on the ground. How many forces are there? N2, N1, friction, mg. Isn't it? That's why there are only 4 forces. Theta. Horizontal direction. N2 is equal to friction. Vertical direction. N1 is equal to mg. Don't write F is equal to mu n1. F is less than equal to mu n1. It is not slipping. We don't know it is F is maximum. It is not on the verge of slipping. We don't know whether F is maximum or not. He simply said it is not slipping. So F can be anything less than mu n. Now take a torque about any point. Which point do you think? We'll take the bottommost point. Torque about A will be torque due to N1, torque due to friction, torque due to mg, and torque due to N2. N1 and F is gone. Now for mg here, extend the line, drop the perpendicular. This distance will be L by 2 cos theta. N2, extend the line and drop a perpendicular. This distance will be L sin theta. So mg का torque will be mg, L by 2 cos theta, k cap. N2, the perpendicular distance is L sin theta minus k cap is 0. From here we get N2 is equal to mg by 2 cot theta. N2 आ गया, friction आ गया. So there, we are done with this. We got all n and f ka values. But they can ask you something more. I know f is less than or equal to mu n1. This is mg by 2 cot theta. N1 is mg. So mu should be greater than or equal to cot theta by 2 for no slipping. They can ask you this question also. Find the minimum coefficient of friction so that the rod does not slip. Check it out. You couldn't have done this question with NLM without the torque. And if you see, the process is still the same. Draw an FBD, force equations, horizontal, vertical, write torque about a point where maximum forces pass through. Equation solved. And this is what I was saying. If you don't know how to calculate torques, the problem, you can't do the problem. So this is the axis now. Extend the line, drop the perpendicular. ये distance L by 2 था. So this is L by 2 cos theta. This is L by 2 sin theta. Check out the perpendicular distances. Ask me any step you're not clear with this. Why did you cancel torque about friction? I hate friction. Normally, that's why I cancel them. Dekho na, why do you think I cancelled it? Because we are anti-friction people. No. F is passing through point area, God. So 0 है ना? वही logic है. Then why did you cancel N1? The same reason, isn't it? Clear, everyone? Got this? Easy. Turn in the page. Let's see something interesting. We have a wooden plank here with a hinge. You are supporting this wooden plank with a block. Think about it. If the plank support is not there, na, this is what would have happened. This is how it looks without support. Making sense? Now, this is x is equal to 0. X is equal to L. So initially the block is at x is equal to L by 2. Mass of the plank is m. Block ka mass is not required. And this is a rough plank. I think here the friction is mu, the ground is smooth. Now what happened? Someone started pulling this block outside with a slowly. The block is pulled out slowly by an external force. How much is the force? We don't know. Find work done by the force in order to pull the block out. Did you get the question scenario? So there is a plank, a block is supporting it. So all the weight is falling on this block. There's a friction between the plank and the block, but there's no friction on the ground. So someone started pulling this block slowly, right? So it is not accelerating, it is pulled slowly by some external force. So initially it is at L by 2. To find the work done by this force to pull this block out under from the plank. Let's see how to do this thing. L by 2. Wrong address. Again, what to do? Step 1, draw the FBD. There's no other way out. Start with an FBD. If you draw the FBD of there are two systems now. Draw the FBD of the block and the plank. If you draw them, I think you'll see something. Take a minute, then I'll show you. See whether you got the FBD right. Ny, Nx, your own weight mg. First thing, let the block be somewhere at x, okay? Always, when you do the problem, since the block is coming out, draw the FBD at an intermediate stage. Let the block be somewhere here at a distance x. Ny, Nx, your own weight mg, normal reaction and friction. There's a friction between the block and this thing. So if you draw the FBD of this thing, you will see the same N is acting here and the same friction is acting here, and this is capital force. On the block, friction is left side. On the plank, friction is right side. Check your FBD. Block ka weight is not important, so we are not drawing it. And ground is anyway smooth, that doesn't matter. So if you take the torque about the hinge,
आपने फ्रिक्शन का क्या बोला?
what did I say? I said on the block it is left side, on the plank it is right side. No?
अच्छा,
Block is coming out, no?
to be the rod. Okay, okay.
The torque due to friction, torque due to N, and torque due to mg. This guy is gone, this guy is gone, this guy is gone. So this would be, N ka distance would be how much? X. Mg ka distance will be L by 2. So this will be N into X k cap plus mg into L by 2 minus k cap is 0. The normal reaction is not constant. The more you pull the block out, the lesser the normal reaction. Think about it. If you have a rod like this, is it more easy to catch here or is it more easy to catch here? The farther you are from the rod, isn't that more easy to hold it?
Yeah.
If you're trying to give support here or if you're trying to give support here, isn't this farther the point, the more easy to catch it? So that means as you're going out, the normal reaction will keep decreasing, isn't it? So the force on this thing keeps decreasing. So the friction will be equal to mu into N. It is maximum because it is slipping. So on this block, we get friction capital F is equal to friction, which is equal to mu into mg L by 2x. This is the force acting on the block since it is moving slowly. Since acceleration is 0, you're pulling the block slowly. Then you're done. The work done ka formula is integral f dx. Mu mg L by 2 integral dx by x. Limits will go from, you're starting from L by 2 to L. This would be mu mg L by 2. This would be ln L minus ln L by 2. Mu mg L by 2 ln 2. Check. That's your answer. So FPD, from there we get the torque, torques we get friction, and frictions we get external force, and from there work done. 3 chapters: NLM, torque, and work. These are how the things got connected. The more you pull the block out, the lesser the normal reaction. Lesser the normal reaction, lesser the friction. So the capital F which you're pulling out, the force is variable. So once you got the force, you can finish the work done from there. Clear, everyone? I hope everyone is getting the hang of FBD's torque and everything. So now you'll get used to finding torques and stuff. So later on, things will start moving. So then it is just one more additional step. Let's see, one more. Turning the page.
This is 1 minute.
Yeah. Done. Who got disconnected? Next one. Last one for the day. We have an incline. The incline is fixed. This is rough. On the incline, we have a solid cylinder. On top of the incline, we have a rod. This is a question from some booklet. So rod ka mass is mass M and length L. Mass of this thing is also M. All surfaces are rough, meaning there's friction even between the rod and the cylinder also. So one end of a rod is hinged and the other end rests on a solid cylinder. Okay, all surfaces are rough. Find friction between a rod and cylinder, cylinder and incline. Let's get this. There's a friction between the rod and the cylinder, and there's a friction between the cylinder and the incline. Find both the frictions. System is in equilibrium. Remember the steps. Draw an FBD, force equations, torque equations, choose a suitable point, solve. So here it will matter which point you're taking. If you can take a proper point, it will make your life easy. You take some other point, you'll get more equations, but you'll be able to solve. Try. You got 3-4 minutes. Start with an FBD. Anyone not clear with the question, please ask me. Just give it a try. I'll be back in a minute. Let's see. Check your free body diagrams first. First the rod. Ny, Nx, your own weight mg, N1, F1. From the cylinder, F1, N1, your own weight mg, N2. Remember, normal should pass to center. F2. Check. Check your FBD. This many forces should be there. 5 forces on each. You messed up the FBD, then it is gone. Now what? If you take for the rod, torque about the hinge, we get a torque due to Nx, torque due to Ny, torque due to F1, torque due to N1, torque due to Mg should be 0. Gone, gone, gone. This is N1 into L, K cap plus Mg into L by 2 minus K cap. We get N1 is equal to Mg by 2. Perfect. Now try. I'll give another minute or two. Now what to do? You need to find F1 and F2. And don't write F1 is equal to mu N1 and don't write F2 is equal to mu N2. That's a blunder. You can write them only when they're slipping. No need to write force equation. Torque equation answer आ जाएगा यहाँ पे. There's one more interesting point here. If you see, torque about the center of sphere. Torque due to N1, torque due to Mg, torque due to N2, torque due to F1, torque due to F2 is 0. This is gone, this is gone, this is gone. You get F1R minus K cap plus F2R plus K cap is 0. F1 is equal to F2. You just need to find one of them actually. Both are equal frictions. If you take about the center, N2 will passing through, Mg is passing, N1 is passing. तीनों गया. F1 F2 का relation आ गया. So if you can just find F1 or F2, my job's done. Can you see there's one more point from where you can get F1 directly? In this diagram, what all things I know? I know N1, I know Mg, right? What I don't know? I don't know N2, I don't know F2. So if you can take torque about this point, N2 will be gone, F2 will be gone. F1 आ जाएगा ना? Making sense? So choosing points properly will save you a lot of time. So by taking about the center, I got F1 is equal to F2, but that still didn't help me out. But if I take about this point, F1 ka value will come. Try, finish it off. I'll take torque about this point and calculate. this problem can be completely solved only with torques. Meaning you could have written force equations. That would have been more lengthy. So you can choose multiple points. Three mg by 2 sine theta. Let me get the distances. So if you want to take torque about this point, this is the center. This is N2. This is theta. This is 90 minus theta. This is theta. So if this distance is r, this distance will be r sine theta. This distance will be r cos theta. And this distance will be r. Friction के लिए चाहिए ना perpendicular distance. So for friction, the perpendicular distance will be r plus r cos theta. So if we talk about this point here, torque about A, torque due to N1, torque due to N2, torque due to F2, torque due to mg, torque due to N1 plus torque due to F1. This guy and this guy are gone. So mg ka torque will be mg into perpendicular distance. That is this distance, r sine theta. Friction ka perpendicular distance, r plus r cos theta. So N1 r sine theta plus mg r sine theta is balancing friction F1 r plus r cos theta. N1 का value तो we already calculated mg by 2. So 3 mg by 2 sine theta by 1 plus cos theta is F1. Once I got F1, I got F2 also. That's what I'm saying. Calculating torque is the most important thing. You should take the distances properly. You are taking distances from point A. Extend the friction vector, drop the perpendicular. Have a look at this. It's a good one. This is how problems will be framed based on torque. So this is the new thing that you learned about today, torque. Remaining FBD, you know, forces, you know, all that stuff, you know. Have a look at this. So next class when we meet, we'll do a few more versions of this, and then we'll do something called toppling, and then we'll also start off with moment of inertia. That will be the second part. So it's all about finding torque right now. Once you guys get comfortable like this, right, finding torque equation, the next part is actually motion that we can handle. Next part we will be doing moment of inertia, and then we'll do no slipping condition. Okay, so that's the last one for the day. So this Friday we don't have a class, so we'll catch up directly again next Wednesday. That's on 3rd of Jan. Okay, so any doubts, anything, stay back and ask. Also free to leave. So have a great new year. And